Tonight, I want to tell you about two spacecraft, but suppose they left Earth more than 50 years ago. They crossed the asteroid belt. They flew past the gas giants. They survived the cold outer reaches of the solar system, where the sun is so distant it looks like nothing more than a very bright star. And then they kept going. Pioneer 10 and Pioneer 11, two of the most precisely built machines humanity had ever created, designed to fly through the solar system with extraordinary accuracy, tracked by the most sensitive radio equipment on Earth, their positions calculated and recalculated using every law of physics that science had confirmed over 300 years. And yet, somewhere out in the deep dark, beyond Saturn, beyond Uranus, beyond Neptune, something began pulling them in the wrong direction. Not dramatically, not visibly. You couldn't see it, you couldn't feel it. The spacecraft themselves registered nothing unusual, but the numbers, the extraordinarily precise, carefully measured numbers that scientists extracted from those faint radio signals, told a different story. Something was tugging on Pioneer 10 and Pioneer 11, something small and constant and unexplained, something that pointed directly back toward the sun, something that had no business being there, according to every equation and every law that physics had established since Isaac Newton first wrote down the rules of gravity more than 3 centuries ago. For 27 years, nobody knew what it was. The anomaly had a name. Scientists called it the Pioneer Anomaly, and for nearly 3 decades it sat at the edge of physics, small enough to ignore, strange enough to haunt, persistent enough to refuse to disappear. Some researchers whispered about dark matter, others invoked extra dimensions of space. A few suggested that perhaps gravity itself worked differently at the edge of the solar system, that Newton and Einstein had both missed something subtle about the universe's fundamental rules. Something so small that it only revealed itself at scales nobody had ever measured before, and for a long time they couldn't rule any of it out. Tonight we are going to follow these two spacecraft from the moment they were built, through the extraordinary things they discovered, into the deep silence at the edge of the solar system, and through the decades-long mystery that made physicists genuinely wonder whether our understanding of the universe had a gap in it, a quiet, small, persistent gap that nobody had noticed before. This is the story of Pioneer 10 and Pioneer 11, and the anomaly that followed them into the dark. Get comfortable. This is going to take a while. The year is 1965. NASA is in the middle of the Apollo program. The moon is the destination that dominates every headline, every budget meeting, every press conference. But inside certain offices at the Ames Research Center in California, a smaller group of engineers and scientists is thinking further, much further. They are thinking about Jupiter. At this point in history, no spacecraft has ever reached Jupiter. No machine built by human hands has ever passed through the asteroid belt, that vast ring of tumbling rocks and debris between Mars and Jupiter, and survived intact on the other side. Nobody knew for certain whether a spacecraft could survive that passage. The asteroid belt, in public imagination, was a wall of collisions and chaos. Film and fiction had depicted it as an almost impenetrable storm of boulders. Engineers and scientists knew the models suggested it was survivable, but the models had never been tested by anything we had actually sent. The proposal that would become Pioneer 10 began as something modest, a small, simple, inexpensive spacecraft by NASA standards that would be the first attempt to reach the outer solar system. If it survived the asteroid belt, it would tell scientists something critical about whether the outer planets could be reached at all. If it didn't survive, it would tell them something important about the asteroid belt itself. The design team, led by Charles Hall at Ames Research Center, had a specific philosophy born from both budget constraints and scientific ambition. Keep it simple, keep it light, make it as precise as possible, and then track it with the most accurate instruments available. Do not clutter it with systems that could fail or introduce ambiguity into the measurements. The spacecraft would not rely on solar panels. The sun would be too distant for solar power to be useful. At Jupiter's distance, solar intensity is only about 4% of what it is at Earth. Instead, Pioneer 10 would carry SNAP-19 radioisotope thermoelectric generators, 4 of them, each one a sealed canister containing plutonium-238, a radioactive isotope that produces steady, reliable heat through natural alpha decay. That heat is converted to electricity through thermoelectric junctions, devices with no moving parts, no mechanical systems to fail, no fluids to leak, simply heat flowing through a junction, producing a voltage. This choice, nuclear power, simple design, no solar panels, high precision, would turn out to matter enormously. Not for the reasons they expected, not for decades. Pioneer 10 weighed 258 kilograms at launch. That is less than 570 pounds. For comparison, a modern full-size passenger car weighs between 1,400 kilograms. The entire spacecraft, its antennas, its instruments, its nuclear power sources, its attitude control fuel, weighed less than a third of an ordinary car. The main antenna was a 2.74-meter parabolic dish, nearly 9 feet across. This dish was the spacecraft's primary connection to Earth. Its size was chosen to maintain a strong enough signal across the vast distances the spacecraft would travel. The engineers understood from the beginning that Pioneer 10 was going to go further from Earth than any machine ever had, possibly further than any machine ever would for a very long time. The dish had to keep the link open. The instruments aboard Pioneer 10 were designed to measure almost everything the outer solar system might throw at it. A meteoroid detector to measure the density of dust and debris, a charged particle detector to measure the intensity of energetic particles in the solar wind and at Jupiter, an ultraviolet photometer to study the distribution of hydrogen in the outer solar system, an infrared radiometer to measure the heat budget of Jupiter, a magnetometer mounted on a long boom to isolate it from the spacecraft's own magnetic field, an imaging photopolarimeter capable of producing images by scanning line by line as the spacecraft rotated, and aboard both Pioneer 10 and Pioneer 11, a golden plaque, Carl Sagan's idea. Frank Drake helped design it, a 6 by 9-inch gold anodized aluminum plate attached to the spacecraft's antenna support struts, designed to convey a message to whoever or whatever might eventually find the spacecraft in the vast dark of interstellar space. The plaque depicted a man and a woman standing before a simplified outline of the spacecraft for scale, a diagram of the hydrogen atom's hyperfine transition, a universal measurement that any civilization with knowledge of atomic physics should recognize, and a pulsar map, charting the positions of 14 pulsars relative to the solar system, pointing home, a diagram of the solar system, showing the spacecraft's origin and trajectory, a representation of a binary number system to convey numeric values. It was a message in a bottle, thrown into an ocean so vast that the word ocean fails to describe it, because even then, the engineers knew these spacecraft were not coming back. After Jupiter, after Saturn, after whatever else they encountered, they would continue outward, out of the solar system entirely, on trajectories that no natural force would meaningfully redirect for millions of years. They would drift, silent, for longer than our civilization has existed, possibly longer than our species will exist. If something found them, if anything found them, the plaque would carry a greeting. Pioneer 10 launched on March 20, 1972. It lifted off from Launch Complex 36 at Cape Canaveral on an Atlas Centaur rocket. The launch vehicle was powerful enough to send Pioneer 10 out of Earth's gravitational influence at a speed that made it, briefly, the fastest human-made object ever launched, achieving a velocity that no previous spacecraft had matched at the time of its departure. Pioneer 11 followed on April 5, 1973, nearly identical to its predecessor in most respects. Same power system, same basic instrumentation, same precise, clean design, but Pioneer 11 was given a slightly different mission profile. After Jupiter, it would be redirected to visit Saturn as well, making it the first spacecraft in history to visit the ringed planet. Two machines, two almost identical spacecraft, heading into the dark. In July 1972, approximately 4 months after launch, Pioneer 10 entered the asteroid belt. At that point, nobody knew what would happen. The theoretical models suggested that the density of material in the asteroid belt was manageable, that a spacecraft could thread through without being struck by anything large enough to damage it. But theory and reality occupy different space, and the asteroid belt had never been tested by anything humans had actually sent through it. The belt spans the region from approximately 2.2 to 3.2 astronomical units from the Sun. 1 astronomical unit, the average distance from the Earth to the Sun, is approximately 150 million kilometers. The asteroid belt is therefore a ring of debris stretching across roughly 150 million kilometers of space. Within that ring are millions of objects, from tiny dust grains to rocks hundreds of kilometers across. But the ring is also vast. The space between the rocks is enormous. The density is extremely low. Models said it was survivable. Pioneer 10 spent the next 7 months crossing it. Every day, the science team at JPL and Ames watched the data streaming in, every instrument reading, every telemetry packet, every signal returning across the growing distance, confirmed whether the spacecraft was intact. The photopolarimeter tracked the density of interplanetary dust at each position along the trajectory. The meteoroid detector logged impacts, small ones, dust-sized particles, nothing damaging. The spacecraft continued. The models held. Pioneer 10 emerged from the asteroid belt in February 1973. Intact, fully functional, the belt was survivable. The first great unknown of outer solar system exploration had been answered. We could reach the gas giants. On December 30, 1973, Pioneer 10 made its closest approach to Jupiter. It came within 130,354 kilometers of Jupiter's cloud tops, roughly one-third the distance from the Earth to the Moon. Traveling at approximately 130,000 kilometers per hour relative to Jupiter, the flyby lasted only hours. But what those hours revealed changed our understanding of the solar system's largest planet almost completely. Jupiter's radiation environment was far more intense than anyone had fully predicted. The planet's magnetic field is approximately 20,000 times stronger than Earth's, and it traps charged particles in radiation belts of extraordinary ferocity. Pioneer 10 passed through these belts during the flyby, and several of its instruments were partially overwhelmed by the radiation. Scientists had known Jupiter had a strong magnetic field. They had not fully appreciated what that field meant for anything passing through it. Pioneer 10 bore the consequences, but it also returned data that no human instrument had ever gathered. Jupiter's Great Red Spot, the ancient storm that had been observed from Earth for centuries, was revealed in greater spatial detail than any Earth-based telescope could achieve. The banded cloud structure, the complex atmospheric dynamics, the sheer scale of everything Jupiter, all of it became more real, more measurable, more present in the data coming back across nearly 800 million kilometers. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, were observed and measured in ways not previously possible. The gravity field of Jupiter was measured with new precision. The radiation belts were mapped in detail that immediately informed the design of future missions. After Jupiter, Pioneer 10 was given a new trajectory by the gravity of the giant planet. The slingshot effect redirected it outward, past the orbit of Saturn, past the orbit of Uranus, past the orbit of Neptune, onto a path that would carry it completely out of the solar system. There would be no more planetary encounters. From this point forward, Pioneer 10 would simply go out and out and out, into the dark between stars. Pioneer 11's story took a different shape. Its Jupiter flyby came on December 2074. Pioneer 11 came even closer to the gas giant than Pioneer 10 had, to within 42,828 kilometers of Jupiter's cloud tops, using that extreme proximity to redirect itself on a completely different arc. The engineers had planned a trajectory that would send Pioneer 11 on a 6-year arc back across the solar system towards Saturn. This required extraordinary precision in the navigation. The gravity assist at Jupiter had to be calculated to set Pioneer 11 on exactly the right path, arriving at Saturn at exactly the right time and angle to achieve a meaningful flyby. On September 1, 1979, Pioneer 11 swept past Saturn at approximately 21,000 kilometers from the cloud tops. Saturn's rings were revealed in new detail. The F ring, a narrow braided ring that had been theoretically suggested but never confirmed, was discovered and measured. The spacecraft passed through the plane of Saturn's rings during the flyby. The engineers had calculated this trajectory knowing it was risky. If the ring plane were denser than models predicted, Pioneer 11 might not survive the crossing. The models held, the spacecraft survived, photographed what it could, measured the temperature and composition of Saturn's atmosphere, and continued outward. After Saturn, Pioneer 11 was heading in the opposite direction from Pioneer 10. Pioneer 10 heading toward the general region of the constellation Taurus. Pioneer 11 heading toward the constellation Aquila. 2 spacecraft, diverging in opposite directions into interstellar space. And both, though nobody realized it yet, experiencing something they were not supposed to be experiencing. Before we get to the anomaly itself, it is worth understanding how NASA tracked these spacecraft, because the tracking method is essential to understanding why the anomaly was so troubling and why it took the form it did. Pioneer 10 and Pioneer 11 communicated with Earth through NASA's Deep Space Network, a collection of massive radio antenna complexes positioned at 3 sites around the globe. Goldstone in California's Mojave Desert, a facility near Madrid in Spain, a facility near Canberra in Australia. The 3 sites are positioned roughly equally around the planet, so that as Earth rotates, at least one station is always facing whatever part of the sky contains the spacecraft that needs to be contacted. The antennas are enormous. The largest are 70 meters in diameter, wide enough that if you drove a school bus across the dish, it would take you more than 10 seconds to cross from one edge to the other. They are pointed with extraordinary precision at targets hundreds of millions and eventually billions of kilometers away, and they are sensitive enough to detect signals of vanishingly small power. The Pioneer spacecraft transmitted at 8 watts, roughly the power of a modest light bulb, and by the time that signal reached Earth from billions of kilometers away, it had spread across an area so vast that the power density at Earth's surface was measured in units far smaller than a billionth of a watt per square meter. The tracking method relied on something called the Doppler effect. When Pioneer 10 or Pioneer 11 transmitted a radio signal back to Earth, the frequency of that signal was precisely known at the source. The spacecraft's transmitters operated at a specific stable frequency, maintained by an extremely precise oscillator. But as the spacecraft moved, either toward or away from Earth, the frequency of the received signal shifted slightly. You know this effect from everyday life. When an ambulance approaches, its siren sounds higher in pitch than when it moves away. The sound waves are compressed by the ambulance's motion toward you, raising the pitch. When the ambulance recedes, the waves stretch out, lowering the pitch. The same physics applies to radio waves. If the spacecraft is moving away from Earth, the signal arrives at a slightly lower frequency than it was transmitted. By measuring this Doppler shift with extraordinary precision, engineers at JPL could determine not just whether the spacecraft was moving, but how fast toward or away from Earth to within fractions of a millimeter per second. This is the precision we are talking about. Fractions of a millimeter per second. For a spacecraft billions of kilometers away, the tracking was made even more precise by a technique called two-way coherent ranging. A signal would be transmitted from Earth to the spacecraft. The spacecraft would lock onto that signal and transmit it back, slightly transformed so the two could be distinguished. And the round-trip timing and Doppler shift of that two-way signal would be measured with nanosecond precision. This allowed not just velocity but distance to be determined to within a few meters, even at billions of kilometers. The precision of this measurement system is what made the anomaly visible, because when you can measure something with this precision, when you can track an object's velocity to within thousandths of a millimeter per second across billions of kilometers, you can detect extraordinarily small forces acting on that object, forces that would be completely invisible to any cruder measurement. The Pioneer spacecraft were specifically well-suited to this kind of precision tracking. They were spin-stabilized. They rotated at a constant rate, approximately 4.8 rotations per minute, which kept them pointed accurately without requiring thrusters to fire frequently. This was important. Every thruster firing would disturb the spacecraft's motion. If thrusters fired randomly or frequently, the trajectory would be full of small disturbances, making it difficult to detect any underlying systematic effect. Pioneer 10 and Pioneer 11 also had simple symmetric designs. They did not carry solar panels that could flex and shift. They did not have large articulated platforms or rotating scan mirrors. Every surface was fixed. Every mass was fixed. Every force should have been predictable. They were, in the language of physicists, extraordinarily clean targets. Objects whose motion should have been predictable with extreme precision, given the known gravitational forces acting on them, primarily the Sun, with precisely calculated corrections for every planet, Jupiter's immense gravity, the Moon's pull on Earth affecting its position in space, the pressure of sunlight on the spacecraft's surfaces, and everything else in the solar system whose mass created measurable gravitational effects. For years, the tracking data matched the predictions, and then gradually, it did not. The first hint appeared in the early 1980s. Pioneer 10 was by this point well past Saturn's orbit, heading outward through the region that would eventually become known as the Kuiper Belt. A navigation engineer and radio science researcher named John Anderson was at JPL working on precise orbital calculations for the spacecraft. Anderson was not looking for anomalies. He was doing the kind of routine precision work that occupied navigation engineers, checking the spacecraft's predicted position against its measured position, maintaining the accuracy of the ephemeris. He found a discrepancy. Pioneer 10 was not quite where it should be. The difference was small, extraordinarily small, extraordinarily small. So small that for a while, the temptation was to attribute it to measurement error, or to some unaccounted for systematic effect in the tracking system, a calibration offset, a timing error, some atmospheric effect on the radio signal that had not been fully corrected. But Anderson was careful. He checked his calculations. He checked them again. He brought in colleagues. He methodically hunted for errors in the force model, errors in the accounting of the Sun's gravity, of Jupiter's gravity, of the gravitational influence of every known body in the solar system, of the pressure of sunlight on the spacecraft. Every source of force he could identify, he checked, corrected where needed, and recomputed. And still, the discrepancy remained. Pioneer 10 was slightly closer to the Sun than it should be, not dramatically, not by a distance you could point to on a diagram and call obvious, but the accumulated effect of years of small, consistent, unexplained deceleration. A tiny force pointing back toward the Sun had produced a measurable deviation from the predicted trajectory. The force was tiny, approximately 8.74 10 meters per second squared. To understand what that number means, the acceleration due to gravity at Earth's surface, what you feel when you stand up, what pulls a dropped object to the floor, is approximately 9.8 meters per second squared. The anomalous acceleration on Pioneer 10 was roughly 10 billion times smaller than the force of gravity you experience right now in this room in this moment. This is almost unimaginably small, 10 billion times smaller than what you feel when you stand up, 10 billion times smaller than what holds you to the surface of the Earth. And yet it was real, and it was consistent, and it had been acting on Pioneer 10 for years. Anderson was cautious. He did not announce a discovery. He continued to gather data. He brought in more colleagues. He widened the analysis to include Pioneer 11, which was on its own trajectory heading in the opposite direction. And Pioneer 11 showed the same anomalous acceleration, the same magnitude, the same direction toward the Sun, the same consistency. Two spacecraft, heading in opposite directions across the solar system, both experiencing an identical unexplained tug back toward the center. That ruled out many easy explanations immediately. If the anomaly were caused by some localized effect, a gas cloud, a region of unusual gravitational density, some asymmetry in the distribution of mass in the outer solar system, you would not expect it to appear identically on two spacecraft traveling in completely opposite directions. Whatever was causing the anomaly did not care which way the spacecraft was pointed. It did not matter which direction of the galaxy the spacecraft was heading toward. It pulled equally on both, always toward the Sun. This made it interesting. This made it, in the language of physicists, a real problem. Anderson published the first formal paper on the anomaly in 1998 in Physical Review Letters, along with colleagues Philip Lying, Eunice Lau, Clifford Liu, Michael Martin-Nito, and Slava Turyshev. The paper's title was careful and precise: Indication, from Pioneer 1011 Galileo and Ulysses data, of an apparent anomalous, weak, long-range acceleration. The word indication, not proof, not discovery, indication. The paper was measured in its claims, transparent in its uncertainties, careful in its language. Something appeared to be there. It needed to be explained. The scientific community took notice. Let's sit with that number for a moment. 8.74 meters per second squared. It is a number with a strange property. It is almost exactly equal to the product of the speed of light, 299,792,458 meters per second, and the Hubble constant, the rate at which the universe is expanding, approximately 2.2 × 10⁻⁸ per second. Multiply those two fundamental constants together, and you get approximately 6.6 × 10⁻⁸ meters per second squared. Multiply by a factor of about 1.3, and you are in the right range. Another way to put it, the anomalous acceleration is suspiciously close to 2 times the speed of light multiplied by the Hubble constant, Ch0 This is the kind of coincidence that physicists do not easily dismiss. When a measured physical quantity turns out to be expressible simply in terms of fundamental constants, that is usually a signal that there is underlying physics connecting them. Random coincidences exist, but they are not usually this clean, this close to simple expressions of known constants. Was the anomaly somehow connected to the expansion of the universe? Could the accelerating expansion of space itself, which acts at cosmological scales to push galaxies apart, somehow manifest as a subtle additional effect at solar system scales? This was one of the earliest proposed explanations. It was not obviously wrong. It would take years and substantial theoretical effort to determine whether it was right. The spacecraft also revealed something important about when the anomaly began. When scientists went back and examined the earliest tracking data from the 1970s, when the spacecraft had not long left Earth, they could find the signature of the anomalous acceleration even then. It was not something that appeared suddenly at some threshold distance from the Sun. It appeared to have been present, constant and quiet, throughout the entire journey. This ruled out a second class of possible explanations. If the anomaly were due to some force that grew stronger with distance from the Sun, as some proposed modifications of gravity predicted, you would expect the anomaly to increase as the spacecraft traveled further out. It did not. It was constant throughout. From just outside the orbit of Jupiter to 80 astronomical units and beyond, the anomalous acceleration measured the same value, 8.74 × 10 meters per second squared. Always, everywhere, in both directions. Pioneer 10, by the time the anomaly was formally published in 1998, was approximately 70 astronomical units from the Sun, 70 times the Earth-Sun distance, roughly 10.5 billion kilometers. At that distance, the Sun's gravitational pull on the spacecraft was already extremely weak. The anomalous acceleration, though tiny in absolute terms, was now a significant fraction of the Sun's gravitational influence at that distance. In terms of accumulated positional error, the total displacement from where Pioneer 10 should have been, based on purely gravitational models, The anomaly had moved the spacecraft approximately 400,000 kilometers closer to the Sun than predicted, across 10.5 billion kilometers. This represents a deviation of less than 0.004%. That is why it took so long to notice, and that is why it was so hard to immediately rule out mundane causes. An error of 0.004% can have many explanations. The challenge was determining which one, but the consistency, the persistence over decades, the same value on two spacecraft heading in opposite directions made it real, not its size, not its direction, its persistence. When the 1998 paper appeared, the scientific community's first response was not excitement. It was skepticism, and that was exactly the correct response. Science does not accept extraordinary claims without first exhaustively hunting for ordinary explanations. The Pioneer anomaly was an extraordinary claim that something new, something unknown to physics, was acting on two spacecraft in the outer solar system. Before accepting that, every conceivable mundane explanation had to be investigated and eliminated. The list of ordinary candidates was long. The first was gas leaks. All spacecraft carry propellant. Pioneer 10 and Pioneer 11 had hydrazine thrusters, small rockets used for attitude control when the spacecraft needed to be reoriented. Hydrazine is stored under pressure and expelled through small nozzles. If a tiny amount of hydrazine were leaking continuously and uncontrolled from the spacecraft, the reaction force, Newton's third law, every action producing an equal and opposite reaction, could produce exactly the kind of small, persistent acceleration that was being observed. This was checked with care. Hydrazine leaks produce a thrust that changes over time as the fuel supply decreases. The anomalous acceleration did not change measurably over the decade it was observed. Furthermore, the thermal signature of a hydrazine leak, the specific heat it would add to particular parts of the spacecraft, would produce a distinctive pattern in the data. That pattern was not present. Diazotylum gas leaks were ruled out. The second candidate was solar radiation pressure. The Sun emits not just light, but a continuous stream of photons, each carrying momentum. When light strikes a surface, it transfers a tiny amount of momentum, a tiny push. This pressure of sunlight creates a real measurable force on any object illuminated by the Sun. It decreases with distance following an inverse square law. At twice the distance from the Sun, the pressure is 1/4 as strong. Solar radiation pressure on Pioneer 10 had been carefully modeled and accounted for in the trajectory calculations from the beginning. At the distances where the anomaly was being measured, beyond 20 astronomical units, the solar radiation pressure was extremely weak. It accounted for less than 10% of the anomalous acceleration, and critically, it would decrease with distance, while the anomaly remained constant. Solar radiation pressure could not account for the Pioneer anomaly. The third candidate was the distribution of matter in the outer solar system. The outer solar system contains interplanetary dust, gas, and as we now know, many small Kuiper belt objects. If the density of this material were higher than our models assumed, the gravitational pull of all that material could pull the Pioneer spacecraft slightly back toward the Sun. This was modeled. The amount of mass required to produce an anomalous acceleration of 8.7410 meters per second squared, distributed in a sphere or shell around the Sun at Pioneer's distances, was calculated. That mass, if it existed, would also have gravitational effects on the planets. It would perturb the orbits of Neptune, Uranus, Saturn, and Jupiter, pulling on them in ways that should be measurable. But the planetary orbits were precisely known. Decades of careful tracking, decades of precise measurements, showed the outer planets following their predicted paths with extraordinary fidelity. There was no sign of the additional gravitational perturbation that the proposed dust and mass distribution would require. Whatever was affecting Pioneer 10 and Pioneer 11 was not affecting the planets. This was a crucial constraint. It meant the anomalous force either was not gravitational in nature, or it was affecting only the Pioneer spacecraft specifically, not every object in the outer solar system. The fourth candidate was systematic error in the tracking data. Perhaps the Deep Space Network was introducing biases. Perhaps the models used to account for Earth's movement through space, Earth's rotation, atmospheric refraction of the radio signals, clock errors in the timing systems. Perhaps one of these corrections was slightly wrong in a consistent way that mimicked a real acceleration on the spacecraft. This was the most technically demanding possibility to rule out. It required a complete audit of the tracking methodology, done independently by multiple teams. Original calibration records from the Deep Space Network from the 1970s and 1980s were recovered and reviewed. Atmospheric correction models were examined. Timing synchronization procedures were documented and verified. Small errors were found here and there, minor corrections that had been applied inconsistently. calibration offsets that had not been fully tracked. Each correction was applied to the data. Each reduced the residual slightly, but none of them eliminated it. Even after applying every correction that could be found, the anomaly remained. The fifth candidate was heat. This was, in retrospect, the most important of the mundane candidates, and it was, in 1998, the most difficult to evaluate. All spacecraft generate heat. Electronics generate heat. Nuclear generators generate heat. And when heat is radiated from a surface into the vacuum of space, the radiation carries momentum. A surface that radiates heat in one direction receives a tiny reaction force in the opposite direction, exactly like a rocket, but extraordinarily weak. If Pioneer 10 and Pioneer 11 were radiating more heat in one direction than the other, if the heat emission were asymmetric, the net force from that asymmetric radiation could produce a persistent acceleration, and because the spacecraft were always pointed approximately toward the Sun, the main dish facing Earth, which is always relatively close to the direction of the Sun from the outer solar system, any excess heat radiated away from the Sun would produce a force pointing toward the Sun. This was exactly the direction of the anomaly, but in 1998 the thermal hypothesis could not be properly evaluated. The original engineering documents for Pioneer 10 and 11 were incomplete. Some records had been archived on tapes that required specific hardware to read. Building a sufficiently detailed thermal model of spacecraft designed in the 1960s and built in the 1970s, using fragmentary documentation, was an enormous task that would require substantial resources and a dedicated effort. The thermal hypothesis was noted, but it could not be confirmed or ruled out without work that hadn't yet been done. When ordinary explanations fail, or when they cannot be properly evaluated, physicists are not embarrassed to consider extraordinary ones. That is the nature of science at the frontier. If the data is reliable and the ordinary explanations are exhausted or unprovable, then what remains, however strange, must be examined honestly. The Pioneer anomaly, by the late 1990s and early 2000s, produced a genuine cottage industry of theoretical papers. Hundreds of researchers proposed explanations. Some were technically sophisticated and carefully constrained by other observations. Some were speculative, some were frankly creative. Here are the serious ones. The first serious extraordinary candidate was modified Newtonian dynamics, or MOND. MOND was proposed in 1983 by Israeli physicist Mordechai Milgrom as an alternative to dark matter for explaining the rotation of galaxies. The core idea was direct but radical. What if Newton's second law, force equals mass times acceleration, is not quite right at very low accelerations? In everyday experience, all accelerations are large compared to Milgrom's threshold value A0, approximately 1.2 × 10 meters per second squared. In these regimes, MOND and Newtonian mechanics agree completely, but at very low accelerations below this threshold, MMG predicts that the effective gravitational force is stronger than Newton predicts. Objects in this regime behave as though gravity is more powerful than the standard equations say. Notice the connection. The Pioneer anomaly acceleration, 8.74 to 10 meters per second squared, is within an order of magnitude of the MMG threshold. The spacecraft at the edge of the solar system was operating in a gravitational environment where the sun's pull produced accelerations approaching this threshold. Could MMG be responsible? In principle, if gravity were stronger than predicted at low accelerations, Pioneer 10 and Pioneer 11 would be pulled toward the sun more strongly than the models predicted. This would appear in the tracking data as an apparent anomalous acceleration toward the sun. It was a mechanism that could in principle produce the observed effect. But MOND made specific quantitative predictions, and those predictions did not match the Pioneer anomaly precisely. The MOND effect at Pioneer's distances and accelerations would not produce exactly 8.74 10^-1. Furthermore, MOND predicted that the anomaly would vary with distance from the Sun, stronger at larger distances where accelerations are lower, and the Pioneer anomaly appeared to be constant. MOND also made predictions about the outer planets' orbits that were not observed. MOND remained a possibility that could be tested but not confirmed by the Pioneer data. The second class of explanations involved dark matter, not the galactic dark matter of cosmology, the vast halos of invisible mass surrounding galaxies, but a specific local distribution of dark matter concentrated within the solar system itself. What if there existed a shell or torus of dark matter centered on the Sun, dense enough to produce gravitational effects on the Pioneer spacecraft, but thin enough not to significantly perturb the planetary orbits? This was technically possible. Dark matter interacts with ordinary matter only through gravity, not through electromagnetic force, which is why we cannot see it. If it were distributed in exactly the right geometric configuration, it might produce a constant gravitational pull on objects at Pioneer's distances while leaving planetary orbits unaffected. Models were constructed. For certain distributions of dark matter, the acceleration produced could match the Pioneer anomaly in magnitude, but each configuration was specific and somewhat arbitrary. There was no physical mechanism that would cause dark matter to naturally arrange itself in the precise shell configuration required to produce a constant, direction-independent pull on Pioneer without affecting the planets. The dark matter hypothesis required fine-tuning that made it feel contrived. The third class of proposals was genuinely exotic, extra dimensions of space. String theory and its various relatives predict that space may have more than 3 extended dimensions, but that the additional dimensions are compactified, curled up into structures so small they are invisible at accessible length scales. In some versions of these theories, gravity, which is mediated by a particle called the graviton, can leak into the extra dimensions. At short distances, gravity behaves normally, but at very large distances, the leakage into extra dimensions could cause gravity to weaken more slowly than the inverse square law predicts. If gravity's behavior changes at large distances, this could appear as an anomalous acceleration on spacecraft at the edge of the solar system. Various extra-dimension models were applied to the Pioneer data. Some could produce effects in the right ballpark. None produced exactly the right number without additional free parameters that could be tuned to fit, and the same modifications that produced the Pioneer anomaly tended to produce other effects on planetary orbits that were not observed. The fourth class of explanations modified inertia itself. What if the relationship between force, mass, and acceleration breaks down at very low accelerations? At very low accelerations in certain theoretical frameworks, an object's inertia might not be constant. It might decrease, meaning a given force produces a larger acceleration than standard mechanics predicts. Seen from outside, this would appear as an anomalous force in the direction of the observed acceleration. Some of these theories could numerically reproduce the Pioneer anomaly. Some could also explain the galactic rotation curves that MOND was designed to address, but they tended to violate conservation laws that were experimentally well established, and they made other predictions that contradicted observations. The fifth candidate was the most conservative of the exotic explanations, an undetected error in general relativity itself. Einstein's general theory of relativity has been tested with extraordinary precision in the strong field regime, near the Sun, near black holes, in binary pulsars whose orbital decay matches relativistic predictions to 10 decimal places. These are regions of strong gravitational fields where relativistic effects are large and easily measured, but the outer solar system is a weak field environment. The gravitational field of the Sun at 70 astronomical units is approximately 5,000 times weaker than at Earth's orbit. The precision with which general relativity had been tested at these scales was far lower. Could general relativity have a small systematic deviation at very low gravitational fields, a deviation too small to be detected in the inner solar system, but detectable at Pioneer's distances? Theorists explored this carefully. Certain parameterized post-Newtonian frameworks could accommodate small deviations from general relativity at low field strengths. Some of these frameworks produced anomalous accelerations of the right order of magnitude, but whenever a specific modification was proposed, other experiments, other measurements in other contexts, constrained it to the point where it could not produce the Pioneer anomaly without contradicting something else. By approximately 2005, the theoretical landscape was this. Many exotic explanations were logically possible, none were compelling without additional assumptions. The mundane explanations had been substantially but not conclusively evaluated. The thermal hypothesis remained unresolved, present as a candidate but unconfirmed, because the modeling work required to evaluate it properly had not yet been done. Pioneer 11's last contact with Earth was September 30, 1995. Its power supply had degraded to the point where it could no longer transmit a detectable signal across the growing distance. It fell silent somewhere beyond Neptune's orbit, heading toward Aquila. Pioneer 10 was more persistent. It continued transmitting, growing fainter every year, its signal stretching thinner as it crossed each new threshold of distance. On January 23, 2003, the Deep Space Network's 70-meter antenna at Goldstone received the last coherent signal from Pioneer 10. At that moment, the spacecraft was approximately 12.23 billion kilometers from Earth, 82 astronomical units. The signal had traveled for approximately 11 hours and 20 minutes at the speed of light before reaching the antenna, and even at that power level, the faint whisper of an 8-watt transmitter across more than 12 billion kilometers, the antenna had picked it up. After January 2003, there was nothing more. The last voice, the last data, the last Doppler shift. Whatever answer existed was already in the archives. In the mid-2000s, a physicist named Slava Toryshev at JPL decided to approach the Pioneer anomaly from a completely different direction. Toryshev had been one of the co-authors on the original 1998 paper. He had worked on the anomaly on and off for years. He had watched as exotic explanations were proposed and constrained. He had watched as mundane explanations were tested and eliminated. And he had become increasingly convinced that the thermal hypothesis, the asymmetric heat radiation idea, had never been properly evaluated. Not because the earlier researchers had been careless, but because doing it properly was genuinely a massive undertaking that nobody had yet committed fully to. Properly evaluating the thermal hypothesis required three things. First, a detailed, accurate thermal model of the Pioneer spacecraft, not a rough estimate of heat output. A precise finite element simulation of every surface, every heat source, every material, every angle of radiation, a model that could calculate to engineering accuracy how much heat was being radiated from each surface of the spacecraft, in which direction, and with what intensity. Second, all available tracking data from both spacecraft, not just the data from the 1990s, but the earliest data from the 1970s, which would reveal whether the anomaly was present from the beginning or developed later. Third, the computational and analytical tools to apply the thermal model to the tracking data and determine whether, once thermal forces were properly accounted for, the anomaly disappeared or some residual remained. The thermal model was achievable but demanding. The tracking data was a different problem entirely. Pioneer 10's early tracking data from the 1970s had been recorded on magnetic tapes. Old magnetic tapes, the kind that required specific tape drive hardware to read, hardware that in some cases was no longer manufactured, that existed only in a handful of places, that needed to be carefully maintained or rebuilt to function. Toryshev launched what became, in effect, an archaeological expedition into the archives of NASA. He and his colleagues contacted former JPL employees, engineers, programmers, navigation specialists who had worked on Pioneer 10 and Pioneer 11 in the 1970s. Some had retired. Some were difficult to locate. Some were extraordinarily helpful. From these people came fragments of engineering documentation that didn't exist in any official archive. Hand-drawn thermal diagrams, internal memos about the RTG performance characteristics, test data from before launch, memories of design decisions that had been made and recorded nowhere in formal documents. They found tapes in storage warehouses, tapes in archives that had not been opened in decades, tapes in people's garages, tapes of uncertain condition, recorded in data formats that software no longer supported, requiring custom readers to be designed and built to access the content. The team spent years on this effort. They recovered approximately 43 years of tracking data, radio Doppler data and ranging data from both Pioneer 10 and Pioneer 11, spanning the period from shortly after launch through the spacecraft's final transmissions. This was more comprehensive Pioneer tracking data than had ever been assembled in one place for analysis. Reading and processing this data required building custom hardware to interface with the old tape drives. It required reverse engineering data formats from incomplete specifications. It required writing software, essentially from scratch, to ingest, decode, and process data recorded in formats designed for 1970s mainframe computers. It was patient. It was exactly the kind of work that does not receive headlines or prizes, but that makes real science possible. In 2005, a landmark paper appeared documenting the full analysis of the recovered data, confirming in precise detail that the anomaly had been present throughout the entire missions of both spacecraft. It had not appeared suddenly at some distance threshold. It had not developed as the spacecraft aged or as their power systems degraded. It was there from the beginning, constant, persistent. But the thermal model was still incomplete. Building it correctly took additional years. Let's think carefully about what Pioneer 10 and Pioneer 11 look like from the perspective of thermal physics. At the core of each spacecraft is a main equipment compartment, a hexagonal box approximately 36 centimeters deep, containing the electronics for communications, data handling, and scientific instrument management. This compartment generates heat as a byproduct of its operation. Electronics always generate heat. Every current flowing through every resistor, every transistor switching states, converts some fraction of the electrical energy into thermal energy. That heat has to go somewhere. In space, with no air to carry it away, it radiates. Mounted on long booms extending from the main body are the SNAP-19 radioisotope thermoelectric generators. 4 booms, 4 RTGs. Each RTG is a cylindrical canister containing a core of plutonium-238, a radioactive isotope that undergoes natural alpha decay at a predictable, steady rate. The decay produces heat continuously, always. It cannot be turned off. The heat flows through thermoelectric junctions and produces electricity. The remainder, which is most of the heat, since thermoelectric conversion is only about 6% efficient, radiates away from the RTG surface into space. At the time of Pioneer 10's launch, each RTG produced approximately 40 watts of electrical power, meaning roughly 630 watts of waste heat per RTG. 4 RTGs, approximately 2,500 watts total of thermal power, radiating away from the spacecraft continuously. Now consider the geometry. The main antenna dish is a large parabolic reflector, 2.74 meters across. It faces in the direction of Earth, which, from the outer solar system, is always roughly in the direction of the Sun. The dish faces forward, approximately toward the Sun. Behind the main equipment compartment, on the side facing away from the Sun and Earth, the RTG booms extend outward. The RTGs are on the anti-Sun side of the spacecraft. Here is the crucial point. Heat radiates from surfaces in all directions. From any given surface, heat radiates according to that surface's temperature, its emissivity, and the geometry of the surrounding environment. The RTGs radiate heat in all directions from their surfaces. Some of that heat goes directly into space. Some of it strikes the back of the main equipment compartment, where it is partially absorbed and partially re-radiated. Some of it may reach the back of the antenna dish, be reflected, and be redirected. The question that Turashev's team needed to answer was specific. After accounting for all these interactions, does more heat ultimately radiate away from the Sun than toward the Sun? And if so, by how much? If more heat radiates away from the Sun, the reaction force pushes the spacecraft toward the Sun. Newton's third law: for every photon radiated away from the Sun, a tiny push toward the Sun. The magnitude of the force depends on the power imbalance. If only 1% of the 2,500 watts of thermal power radiates preferentially in the anti-Sun direction, that's 25 watts of effective directional radiation. The force produced by 25 watts of directional electromagnetic radiation is approximately 25 newtons, which is about 8.310 newtons. Divide by Pioneer 10's mass of 258 kilograms, and you get an acceleration of approximately 3.2 meters per second squared. This is in the right ballpark, the right order of magnitude for the Pioneer anomaly, but the exact calculation required the full thermal model, not order of magnitude estimates. The actual number derived from the actual geometry, actual material properties, actual power levels. This is what Turashev's team built, using the original engineering drawings, the test data recovered from the archives, the memories of Pioneer engineers, and sophisticated finite element thermal analysis software. They constructed a three-dimensional thermal model of the spacecraft, every surface, every interface between components, every material with its specific emissivity, absorptivity, and thermal conductivity, the RTGs with their measured power output at launch and their calculated decay over time, the main electronics compartment with its dissipation profile. The antenna dish has both a reflector and a thermal radiator. The model was large, running it required significant computing resources. Validating it required checking it against every available measurement from the actual spacecraft. The temperatures recorded by onboard thermal sensors, the electrical power output of the RTGs as a function of time, the thermal behavior during known events. The team ran the thermal model. They calculated the net thermal radiation force on the spacecraft as a function of time throughout the entire missions of Pioneer 10 and Pioneer 11. They applied that force to the trajectory, subtracting its effect from the tracking data, and then they looked at what was left. The paper was published on April 19, 2012. Physical Review Letters. Title: Support for the Thermal Origin of the Pioneer Anomaly. Authors: Slava G. Turashev, Viktor Titov, Gary Kinsella, Siu-Chun Lee, Xing-Mul Lok, and Jordan Ellis. The finding: when the thermal forces produced by asymmetric heat radiation from Pioneer 10 and 11 were properly modeled and subtracted from the tracking data, the anomalous acceleration, the decades-long unexplained tug toward the Sun, disappeared. Not partially, not approximately. The thermal model accounted for essentially all of the Pioneer anomaly within the uncertainties of the model. The physical mechanism was this. The RTGs mounted on the 4 booms behind the main equipment compartment radiated heat outward in all directions from their cylindrical surfaces. Because of their position behind the main spacecraft body, a significant fraction of this heat radiated away from the Sun, away from the antenna dish side. This preferential backward radiation produced a net thermal force pointing toward the Sun. Additionally, heat radiated from the back of the main equipment compartment, struck the interior surface of the antenna dish, which acted as a partial reflector. Some of this heat was reflected forward toward the Sun, which partially counteracted the thermal force. But the net effect, after accounting for the geometry of the dish and the reflective properties of its surface, still produced a preferential radiation of heat away from the sun. The combination of these two effects, RTG backward radiation and equipment compartment forward reflection, produced a net thermal force pointing toward the sun. And the magnitude of that force, calculated from the thermal model with the actual power levels and actual geometry of the spacecraft, matched the Pioneer anomaly. The anomaly was heat. Specifically, it was the warmth of the nuclear fuel that had kept Pioneer 10 and Pioneer 11 alive for 30 years, radiating asymmetrically from the back of each spacecraft, pushing them gently and persistently toward the sun, across billions of kilometers for decades. There was no dark matter, no modification of gravity, no extra dimensions, no unknown force, no gap in general relativity, no crack in Newton's laws. There was heat, the most ordinary thing in the universe, the unavoidable consequence of powering a machine with nuclear fuel, the thermal physics that operates in every electronic device you have ever owned, at every temperature scale. Following rules that have been understood since the 19th century, physics had survived, the laws were intact, the anomaly was explained. It is tempting, when you hear that the Pioneer anomaly was caused by thermal radiation, to feel a small deflation. The exotic explanations were more interesting. Dark matter in the solar system, modified gravity, extra dimensions of space. The mundane answer, heat from the spacecraft's own power source, feels like a letdown. But that reaction is worth examining, because what actually happened over those 27 years is one of the finest examples of how science operates at the frontier, demonstrated in slow motion over nearly 3 decades. Something was observed that didn't fit the models. The observation was carefully documented and cross-checked. It was published, with appropriate uncertainty, as a problem requiring explanation. The scientific community took it seriously, not by immediately accepting new physics, but by systematically investigating every conceivable explanation. Mundane candidates were tested rigorously and either eliminated or constrained. Exotic candidates were explored with comparable rigor and found to be possible but insufficiently compelling. A years-long archival effort recovered data from old tapes that no one had examined in decades. A detailed thermal model was built from fragmentary documentation and the memories of engineers who had retired. The model was applied to the data. The anomaly disappeared. 27 years. That is a long time. But it is not a failure of science. It is what science looks like when the problem is genuinely hard. The required tools don't yet exist, and the community proceeds carefully rather than rushing to a conclusion. What would have been a failure? Accepting the thermal explanation in 1998 based on the rough estimates that suggested it might account for part of the anomaly. Those early estimates were incomplete, and they suggested that thermal effects could account for maybe half the anomaly, leaving a residual that would still require explanation. Taking that incomplete result seriously would have been wrong. The thermal model that finally resolved the anomaly required the full detailed computation that took years to develop. What would also have been a failure, accepting one of the exotic explanations before the mundane ones were exhausted. The scientific community did not do that. Researchers proposed MOND, dark matter, extra dimensions, modified inertia, post-Newtonian corrections, and in each case they tested these proposals against other available constraints. None passed those tests. The community held the anomaly as genuinely open until the thermal work was complete. The Pioneer anomaly also produced a specific, practically important lesson for spacecraft design. When designing spacecraft intended for precision tests of gravity at large distances from the Sun, or any spacecraft whose trajectory must be known with extreme precision, thermal forces must be explicitly modeled and managed. In the 1970s, the precision of orbital tracking was not high enough to detect asymmetric thermal radiation effects. Pioneer's designers simply didn't need to worry about it. The tracking wouldn't be sensitive enough to see a discrepancy of that size. But by the time the thermal effect was large enough to see in the data, and the tracking technology had improved enough to detect it, the spacecraft had already been built and launched. It was too late to redesign the thermal management. Future spacecraft designed for precision geodesy and gravitational science now include explicit thermal management as a design requirement. The heat from electronics and power systems is managed to be as symmetric as possible. Thermal forces are included in the error budget. The Pioneer anomaly, once explained, became a design lesson for every precision spacecraft that followed. The original 1998 paper on the Pioneer anomaly included data from 2 other spacecraft, Galileo and Ulysses. These missions had also shown anomalous accelerations, and their inclusion in the paper broadened the apparent scope of the anomaly. 2. Galileo was a Jupiter orbiter. Launched in 1989, it used Earth for a gravity assist in December 1990, and during its long cruise to Jupiter, its tracking data showed an anomalous acceleration of similar magnitude to Pioneer's. Ulysses was a mission to study the Sun from high solar latitudes. It flew in an orbit that took it far above and below the plane of the solar system, passing over the Sun's poles. Ulysses also showed anomalous acceleration signals in its tracking data during certain phases of its trajectory. But Galileo and Ulysses were very different spacecraft from Pioneer 10 and 11. Galileo had large spinning solar panels, two large fan-shaped panels that rotated relative to the main spacecraft body. Solar panels of this design have complex thermal properties. Heat is absorbed and re-radiated from different surfaces depending on their orientation relative to the Sun and the rotation state. The complexity of Galileo's thermal environment made it far harder to model than Pioneer's clean, simple design. Ulysses was similarly complex. It had solar panels. Its orbit carried it into very different solar radiation environments at different phases. For both Galileo and Ulysses, the precision of the anomaly measurement was considerably lower than for Pioneer. There were more unmodeled forces, more complex geometries, more potential systematic effects. Their data was suggestive. It supported the existence of some anomalous effect, but it was not clean enough to constrain the problem as sharply as Pioneer's data. The Cassini spacecraft provided particularly interesting evidence. Cassini, the Saturn orbiter that operated from 2004 to 2017, was one of the most precisely tracked spacecraft ever flown. During its cruise phase to Saturn, its tracking was analyzed for signs of an anomalous acceleration. Cassini did not show the Pioneer anomaly. This was actually a crucial piece of evidence. If the anomaly were due to new physics, dark matter, modified gravity, some universal force field acting on all objects in the outer solar system, it should appear in Cassini's data just as it appeared in Pioneer's. Cassini's null result strongly suggested that the anomaly was something specific to the Pioneer spacecraft, their geometry, their power system, their thermal design, rather than a universal physical effect, which is exactly what the thermal explanation ultimately confirmed. Cassini had different geometry. Its thermal radiation was more symmetric. Its effect was different from Pioneer's, and the thermal force on Cassini pointed in a different direction relative to its trajectory. The Cassini null result was a quiet but powerful piece of evidence in favor of a spacecraft-specific explanation, and therefore against new physics. Pioneer 10 is still out there. As of 2026, Pioneer 10 is approximately 136 astronomical units from the Sun. That is 136 times the Earth-Sun distance, roughly 20.3 billion kilometers. To cover that distance, light must travel for approximately 18.8 hours. If you stood at the Sun and shouted toward Pioneer 10 at the speed of light, your shout would arrive more than 18 hours later, and any reply would take another 18 hours to return. A simple conversation would take nearly 2 days just for the exchange of a single question and answer. Pioneer 10 is moving at approximately 12.04 kilometers per second relative to the Sun. This sounds fast. It is extraordinarily fast by human standards. 12 kilometers in 1 second, more than 43,000 kilometers per hour. But the universe is large. Pioneer 10 travels about 380 million kilometers per year, slightly less than 2.5 times the distance between Earth and the Sun. Even at this speed, reaching the nearest star system, Alpha Centauri, 4.24 light-years away, would take approximately 74,000 years. Pioneer 10 is not heading toward Alpha Centauri. It is heading toward the constellation Taurus. Specifically, it is on a trajectory that will bring it into the general vicinity of the red giant star Aldebaran in approximately 2 million years. At that point, Aldebaran will be approximately 65 light-years from its current position. Pioneer 10 will pass through the region of space Aldebaran currently occupies, but by then, Aldebaran will have moved. The paths will not intersect. Pioneer 10 is silent. It has been silent since January 23, 2003. Its power supply, the plutonium-238 in its 4 RTGs, has decayed over more than 50 years to the point where it can no longer generate enough electricity to power even the most minimal transmitter. The spacecraft itself is almost certainly intact. There is nothing in the thin interstellar medium to damage it. No atmosphere to create drag. No meaningful radiation environment to degrade its materials beyond the slow march of cosmic ray bombardment, which over millions of years will alter surface properties but will not destroy the spacecraft structurally. Pioneer 10 will drift for billions of years, silent, carrying its plaque, still on the trajectory Jupiter's gravity gave it in December 1973, and still, in the accumulated arithmetic of its position, about 400,000 kilometers closer to the Sun than the original models predicted because of the warmth of its own engines. Pioneer 11 is heading in a different direction, approximately 107 astronomical units from the Sun in 2026, moving at approximately 11.4 kilometers per second toward the constellation Aquila, silent since September 30, 1995. Its trajectory will bring it into the general vicinity of the star Lambda Aquila, a hot blue-white star about 125 light-years away in approximately 4 million years. Again, no actual encounter, just a passing through a region of space. Between them, Pioneer 10 and Pioneer 11 are traveling in nearly opposite directions. They are now separated by approximately 40 billion kilometers, and the distance grows by roughly 23 kilometers every second. In 2 million years, if the human species still exists in any form that can look up at the night sky and consider these things, there will be no way to locate Pioneer 10 or Pioneer 11. The precision of our 1970s trajectory calculations will have accumulated enough uncertainty over 2 million years that the spacecraft could be anywhere in a region of space, tens of billions of kilometers across. They will be effectively lost, not destroyed, but unfindable. The gold anodized aluminum will survive the interstellar medium for billions of years without significant degradation. The engraving will survive. The man and the woman with the raised hand, the hydrogen atom, the pulsar map, the solar system diagram, all of it will still be there, readable, if something ever finds it. That is perhaps the most extraordinary thing about Pioneer 10 and Pioneer 11. They are not dead, they are not lost. They are simply silent and unreachable, gone into a distance that has no human scale, carrying a message that will outlast everything we have ever built. The Pioneer anomaly is solved. But in the course of investigating it, physics noticed something else that is not. The flyby anomaly. When spacecraft use a planet's gravity for a trajectory change, a gravitational slingshot, there is a well-understood calculation for how the spacecraft's velocity should change. The spacecraft falls toward the planet, accelerating as it approaches, swings around the planet at closest approach, and departs on a new trajectory with a new speed. The entire interaction is governed by conservation of momentum, Newtonian mechanics, and general relativistic corrections. The prediction is exact, the math is well understood, and yet in several documented cases, the spacecraft's measured velocity after the flyby has been slightly different from predicted. The near spacecraft flyby of Earth in January 1998, approximately 13.46 millimeters per second faster than predicted. Galileo's 1990 Earth flyby, 3.92 millimeters per second anomalous. Rosetta's 2005 Earth flyby, 1.82 millimeters per second. Cassini's 1999 Earth flyby, essentially zero. Messenger's 2005 flyby, essentially zero. Juno's 2013 flyby, essentially zero. Juno's 2013 flyby, essentially zero. One-day standards, the pattern is inconsistent. Some flybys show anomalies, others don't. John Anderson and colleagues proposed a formula in 2008 that could approximately reproduce the observed anomalies based on the geometry of the encounter, specifically the incoming and outgoing angles relative to Earth's equatorial plane. But nobody knows what physics underlies the formula. Thermal radiation doesn't explain it cleanly. The inconsistency between flybys makes a single universal mechanism hard to identify. The flyby anomaly remains open. It is not as dramatic as the Pioneer anomaly was at its peak. It is messier, inconsistent, smaller, harder to pin down. But it is real, and it does not have an answer yet. Two spacecraft, launched in the 1970s, a tiny anomalous force discovered in the 1980s, nearly 3 decades of investigation, a 2012 paper that solved it with heat. The first lesson: mystery is productive. The Pioneer anomaly was not manufactured, not misunderstood, not inflated. It was a genuine gap between observation and theory. During the period it was open, it generated real scientific work, new data analysis methods, new theoretical proposals, better understanding of how to model spacecraft forces, deeper examination of what precision tracking can and cannot tell us. The mystery produced useful science even before it was resolved. The second lesson: precision reveals things that imprecision hides. When the Deep Space Network improved to the point where fractions of a millimeter per second could be measured across billions of kilometers, the thermal force that Pioneer's designers never needed to worry about suddenly became visible. Some of what precision measurement reveals is genuinely new physics. Some of it is old physics acting at scales that previously didn't matter. You cannot know which you're looking at until you've investigated completely. But Munko, the thermal model required recovering magnetic tapes from warehouses, rebuilding hardware to read them, reverse engineering software to process them, and contacting engineers who had worked on a program 40 years earlier. This is not the kind of work that generates excitement or receives headlines. It is archival, meticulous, unglamorous, and it is exactly the kind of work that solves genuinely hard problems. In 2026, Pioneer 10 is 136 astronomical units from the Sun. The Sun, at that distance, is a star among stars. Still the brightest, still recognizable, if you knew where to look, but no longer the overwhelming presence you know from Earth. A bright point source, the star that keeps the inner planets warm, the star that gave the Pioneer spacecraft their power, and whose gravity gave Jupiter's fly-by the geometry to send them outward. Pioneer 10 cannot perceive any of this. It has no functioning instruments, no camera, no transmitter producing signal. It is a machine now without senses, navigating nothing, carrying everything. Its plaque, its accumulated story, the precise measurement of the anomaly that followed it, the answer that took 27 years to find. The answer was warmth. The heat of plutonium-238, decaying quietly in 4 small canisters, radiating asymmetrically from the back of the spacecraft, pushing it gently toward the Sun for 30 years. Not new physics, not dark matter, the most ordinary thing, a warm object radiating in an imperfectly symmetric way. There is something in that which bears holding for a moment. We built 2 machines to go further than any machine had gone. We powered them with heat, with the slow, steady decay of radioactive material, giving them life for 30 years in the cold dark, and the heat that gave them life followed them outward. It pushed them, gently, constantly, in the direction of home, not enough to bring them back. Nothing will bring them back, but a small force, persistent and quiet, pointing toward the Sun, toward us. A warmth that followed them into the dark for 30 years before it faded. The anomaly was not a mystery of the universe. It was a consequence of ourselves. The warmth we put into machines and sent away. The warmth that the machines carried with them, radiating into the dark, pushing them just slightly in the wrong direction, or the right direction, depending on how you look at it. There is a concept in space science called the termination shock. Solar wind, the continuous stream of charged particles flowing outward from the Sun, fills the solar system in all directions, thinning as it goes but present everywhere inside the heliosphere. At some distance from the Sun, the solar wind loses enough energy that it can no longer push against the pressure of the interstellar medium, the thin gas and particles filling the space between stars. Where the solar wind meets that counterpressure and slows suddenly to subsonic speeds, that boundary is called the termination shock. Pioneer 10 crossed the termination shock in the 1980s. Pioneer 11 did as well, but these spacecraft did not carry instruments designed to detect it. The significance of the termination shock was not fully understood at the time of their launches. They crossed it without reporting what they found there, because they lacked the instruments to report it. It was Voyager 1 that first crossed the termination shock with instruments designed to measure it, in December 2004 at approximately 94 astronomical units. Voyager 2 followed in August 2007. The Voyager spacecraft reported on what they found there, a region of compressed, turbulent, heated solar wind, slowed from supersonic to subsonic speeds, over a boundary that was not a sharp line but a broad dynamic zone. Beyond the termination shock is the heliosheath, a vast bubble of slowing solar wind, compressed against the interstellar medium. Beyond the heliosheath is the heliopause, the true boundary of the Sun's dominion, where the solar wind effectively ends and interstellar space begins. Voyager 1 crossed the heliopause in August 2012. Voyager 2 followed in November 2018. Pioneer 10 and Pioneer 11 crossed into these regions too. We simply couldn't hear them when they did. 2 explorers who walked through the frontier door in silence, unable to send back word of what they encountered. There is a particular kind of loss in that, not grief. The spacecraft did exactly what they were designed to do, but something like the feeling of a letter that arrived too late. They were there. They crossed boundaries no machine had crossed before, and we couldn't hear them when they did it. Pioneer 10 and Pioneer 11 were not the most sophisticated spacecraft ever launched. They were not the most expensive or the most capable. They carried fewer instruments than the Voyagers that followed them. Their images were primitive by modern standards. The photopolarimeter produced pictures by scanning one line at a time as the spacecraft rotated, assembling an image over many minutes. But they were first through the asteroid belt, first to Jupiter. Pioneer 11, first to Saturn, first human-made objects to achieve escape velocity from the solar system entirely. And their anomaly added something to their legacy that nobody planned, a lesson embedded in their data that required 27 years of careful work to extract, a lesson about the limits of our models, about the importance of knowing what forces act on a spacecraft, all forces, including the warmth of its own power source, about the process of science when the answer is not obvious and the tools to find it don't yet exist. The lesson reached forward into the design of future spacecraft. Every precision mission designed after 2012, every mission whose scientific goals depend on knowing the spacecraft's trajectory with extreme accuracy, now carries explicit thermal management as a design requirement. The Pioneer design left heat sources at the back of the spacecraft, radiating asymmetrically because the engineers didn't need to worry about it. Future spacecraft do need to worry about it, and they do. 25 result. This is how engineering knowledge accumulates, not always from successes, sometimes from the questions that take 27 years to answer. We do not know everything about the solar system. This is obvious. But the Pioneer anomaly demonstrated something more specific. We do not always know what we don't know. For nearly 3 decades, the anomaly existed in a space that was neither clearly explained nor clearly mysterious. The thermal hypothesis was always present as a candidate, but without the tools to evaluate it properly, it couldn't be confirmed or dismissed. The anomaly remained genuinely open, something that might resolve to mundane physics, but might equally represent a gap in our understanding of fundamental laws. Living with that ambiguity, holding it seriously without overreacting to it, is one of the harder skills in science. The Pioneer anomaly community managed it well. They published findings with appropriate uncertainty. They proposed exotic explanations while clearly noting that mundane ones remained unevaluated. They pursued the mundane explanations with the rigor they required. They waited for the tools. There are open questions in physics right now that exist in the same conceptual space, things that don't fit cleanly, small discrepancies, tensions between measurements and predictions that might be systematic errors or might be something new. Most of them will resolve to mundane explanations. A few may not. The practice the Pioneer anomaly teaches is the same in all cases. Investigate carefully, eliminate what can be eliminated, build better tools when the existing ones aren't sufficient, and wait, not passively, actively wait, gathering data, improving models, recovering what can be recovered from archives. But wait, without rushing to conclusions in either direction. That patience is one of the distinguishing features of good science at the frontier, and it is available to anyone. It doesn't require a laboratory or a spacecraft. It just requires a willingness to sit with a question, hold it seriously, and keep working. Tonight, Pioneer 10 is out there. Not dramatically, not visibly. You cannot look up at the sky and see it. It reflects no sunlight at useful intensity. It emits no detectable signal. It is the size of a large bicycle wheel, and it is located 20 billion kilometers away, but it is there, moving at 12.04 kilometers per second, silent, carrying its plaque, slightly warmer, still, on the side that faces away from the sun, though the warmth now is only the residual glow of plutonium-238 that has been decaying for more than 50 years. Somewhere in the accumulated arithmetic of its position is the legacy of 8.74 twin meters per second squared, a tiny force that acted on it for 30 years, shifted its position by 400,000 kilometers across a journey of billions, made physicists wonder for 27 years whether gravity had a secret, and was finally explained by the warmth of its own engines. The mystery was small and quiet. The explanation was smaller and quieter. The universe did not announce this anomaly with drama. It hid it in the decimal places of a Doppler shift measurement, in the archives on old magnetic tapes, in the engineering drawings of a spacecraft built in the 1960s. And the answer was there the whole time, in the heat, in the geometry, in the physics of surfaces radiating into the void. Most mysteries are like this. Not dramatic gaps in reality, quiet discrepancies in precise measurements, things that require recovering old data, building better models, consulting people who worked on a project 40 years ago. The universe's secrets tend to be specific. They tend to be in the details. They tend to require exactly the kind of careful, patient, unglamorous work that science does best when it is doing its job correctly. Pioneer 10 is at 1006 astronomical units. In 2 million years, it will pass through the region of space that Aldebaran currently occupies. Aldebaran will have moved. Nothing will happen. Pioneer 10 will continue outward into the next 2 million years of dark. The plaque is still there. The man and the woman, the hydrogen atom, the pulsar map pointing home, gold anodized aluminum, designed to survive the interstellar medium for billions of years. The greeting will outlast the civilization that sent it, perhaps by a lot, perhaps by enough that the destination of that greeting, if it ever reaches one, will find only evidence of something that once existed, without any remaining trace of what became of it. That is a long way to carry warmth. but the warmth followed it. It always follows. Sleep well tonight. Pioneer 10 is still going,